Welcome back. Good afternoon to all. Before we start our next presentation, I would like to invite Dr. Malcolm Dunstan, longest serving member on the ICOL Committee on Concrete Dams and chairman of the committee that drafted ICOL Bulletin 109. He wants to clarify 2 points raised by the first presentation, which was being presented by Mr. Michael Roger this morning. So I would like to invite Dr. Malcolm Dunstan.
Okay, thank you very much. Good afternoon, ladies and gentlemen. I wanted just to clarify 2 points following Mike Rogers' excellent presentation this morning. The first one is Applicability in Greece, where he showed some RCC used to protect the left abutment downstream of the dam where the Nestos River took a turn to the right. My firm designed Platonovacy for the Public Park Corporation of Greece, and I wanted to confirm that the facing concrete was used on the outside of the RCC. That was not only used to protect the plunge pool, but was also used to stabilize the slope above. However, this was constructed back in 1996, and if we were to doing the same again today, we'd be using GEVR against a step slope rather than the sloping slope we used before. And the second point was external membranes on the upstream face of dams. And the question was also raised about this. He showed a photograph of it being used on the San Vicente dam raise. I'd like to confirm that less than 2% of all RCC dams have used an external watertight membrane. And I agree with him when he said that we should design the dam, an RCC dam, to be impermeable. However, external membranes have been retrofitted on a number of RCC dams that have been found to leak. And these are the points I wanted to raise. Thank you very much.
Thank you, Dr. Malcolm Dunstan, for illuminating explanation. Now we move further for the next presentation by Mr. Francisco Ortega on materials and mix proportioning. Let me introduce briefly about the speaker. Mr. Francisco Ortega is a consulting engineer specializing in the design and construction of RCC dams. He graduated in civil engineering from the Polytechnic University of Madrid, Spain, and throughout his career, he has gained large experience as a contractor and as consultant. Since 1999, he has been running Force Consulting Engineering based in Germany. He has extensive experience relating to concrete mix design, optimization, and logistics of RCC production, transportation, and placement on major RCC dam projects. Mr. Ortega has successfully developed, first time in the world, the application of immersion vibrated RCC mixes, bringing significant improvements and economy to modern RCC dam projects. He is member of the Spanish and the German National Committee on Large Dams, and during the last 30 years has been directly involved in the design and construction of more than 50 RCC dams throughout the world. Now I request my colleague to play the recorded presentation received from Mr. Francisco Ortega. Over to the IT department, please.
Good morning, ladies and gentlemen. Thank you to the Indian National Committee of ICOL for the organization of this event, and grateful thanks for your kind invitation to take part in this virtual workshop on applicability and feasibility on RCC dams. The title of my presentation is Materials and Selection of RCC Mixture Proportions. We will focus on latest developments related with the subject that are discussed in chapters 3 and 4 of the new ICL Bulletin number 177 on RCC dams. Since the previous bulletin was published by ICL back in 2003, a number of trends have been observed in the specifications of the materials and mixes that are used to build new RCC dams, and that, generally speaking, improve the in-situ quality of the concrete and provide higher efficiency and economy to the construction of modern RCC dams. This is the list of main topics included in the presentation. After a brief introduction, some key specifications of cementitious materials, aggregates, and most commonly used admixtures will be discussed. Then, details of the RCC workability and consistency test are presented, followed by a summary of the typical mixture proportions for different mix design approaches. Special attention will be given to the recent and successful development of immersion vibrated RCC mixes. Finally, typical mix parameters will be discussed schematically before drawing some conclusions. Introduction. In this introduction, we'd like to give attention to the fact that the use or not of a supplementary cementitious material, SCM, in the mix, these are, for example, fly ashes, natural puzzolans, or slag, that such use or not will guide them to the most probable dam design approach followed by the designers. As discussed in the introduction of the bulletin, two primary dam design approaches for RCC dams can be followed. First, the separate approach, where the RCC mix will not have by itself enough in-situ quality required for a concrete dam, and thus not just RCC but bedding mixes are additionally placed on the joints between the layers to give bonding strength. In addition, some kind of a watertight element is required on the upstream face to provide impermeability to the dam. RCC mixes in a separate approach make no use of SCMs, or very little. They have the main disadvantage of the less efficient placement, with more sophisticated planning of a greater number of activities running at the same time during construction. Therefore, typically, slower production and higher overall cost are associated with this design option. On the other hand, the RCC mix in an all RCC dam approach will make extensive use of fly ash or pozzolan, any kind of SCM, and the mix can be designed to achieve by itself and without bedding mixes and without upstream elements the desired strength between layers and the required impermeability for the concrete dam. This must be recognized as the simplest and most efficient methodology for the construction of high-quality concrete dams. RCC types are also classified by the total content of cementitious materials in low, medium, and high cementitious RCC, with respective limits in 100 and 150 kilogram per cubic meter as indicated in the table. Some typical strength values at 1 year age are included in the table for each type. This table is a summary published in the new RCC bulletin. The lower values of the column at the left side corresponds to low cementitious, less than 100 kilogram per cubic meter, which is mostly associated with the RCC mixes used in the separate dam design approach. On the right column, you can see the values associated with the high cementitious mixes that are typical of the more efficient all RCC dam approach. As can be imagined, a wide range of possibilities for projects with less demanding mixes is also available in the medium cementitious mix in the middle of the two. But before moving into the description of materials, it should be recalled that the ICOLD Bulletin 165 on the selection of materials for concrete dams, published in 2013, addresses the primary selection requirements for materials for all mass concrete dam types, including RCC. And therefore, only issues of particular importance in respect of current RCC practice are addressed in the new bulletin on RCC dams and in this presentation. Cementitious materials. Laboratory testing of different potential sources of cementitious materials is necessary at an early stage of the planning done by the designer to ensure that the concrete performance meets the design criteria. This diagram shows the proportions of the main chemical components of Portland cement and various supplementary cementitious materials. Low lime fly ash type F and natural pozzolans are by far the preferred ones. Aggregates. Let's have a look at the combined gradations of the aggregates for RCC. The typical combined gradations ranges of aggregates used in high and low cementitious RCC mixes are indicated in the table. And we have also represented them in this figure. In red one, you have the high cementitious RCC, and the blue dotted is the low cementitious RCC mixes. Let's have a look at three main points in these gradation curves. First, there has been a clear trend in recent years to reduce the maximum size of aggregate from 80 millimeters or even higher, used in early times, down to 50 or 40 millimeter. The aim is the need to control segregation, especially in the low workability mixes and for rounded aggregates. Second, a slight higher percent of the sand or fine aggregate in the low cementitious content RCC, LC-RCC, compared with the high cementitious RCC that you can appreciate here in the figure. And number three, at the bottom of the curves, the increased amount of non-plastic fines below 75 microns in any type of RCC. Non-plastic in the medium and high cementitious RCC, and some plasticity might be accepted in the low cementitious RCC under certain limitations. This figure shows the individual and combined gradation curves of aggregate for a high cementitious RCC mix. The aggregate split of the combined gradation, shown in black, is 30%, 35%, 35% based on two coarse aggregates, 40 to 20 and 20 to 5 millimeters, represented in red and green color respectively. and one fine aggregate in blue with a high proportion of fines in it, between 12 and 18% in this example. In this figure, a second fine aggregate grading is also shown in brown, which corresponds to a typical natural washed sand that was used for conventional concrete in the same project. The difference between the RCC fine aggregate in blue and the CVC in brown can be clearly appreciated in both the shape of the curve and the significant difference in the area of the fines at the right bottom. In fact, this example gradation is from a recent RCC project involving almost 3 million cubic meters of high cementitious RCC. The picture shows the large aggregate treatment plants installed in two stages, first at the top and the final layout at the bottom. The source of material is not ideal. Alluvium deposits with natural rounded particles and some plasticity in the fines with a relatively high natural silt content. The initial mix design efforts with such materials were not very promising, and first mixes exhibit a relatively high water demand to achieve the desired consistency, without avoiding a significant problem of segregation in the mix. A modification was proposed in the specification of the aggregates, aiming specifically to improve these two issues. First, the less rounded coarse aggregate to control segregation, and second, the production of better shaped crushed fines to reduce the amount of natural fines that were demanding a high water content in the mixes. And this is the result in terms of coarse aggregate. From the proposed new specs, three key aspects have been listed here. First, the 80 to 90% of coarse aggregate that should have been crushed at least in one phase. This is a view of the final fine aggregate in the main stockpile, a combination of natural and crushed fines with a well-controlled gradation in blue in the plot above. And for this material, the void content has been limited to a maximum of 32%, average below 30%, and the specific gravity and absorption values have been systematically checked as a way to control the percent of natural silt in the blend of fine aggregate. The figure shows the reduction of the water content of the RCC mix with the time as the aggregates were improved in the different stages of the mix design process. You can see stages A, B, and C on the bottom axis. The range of consistency of the mix is indicated in the left axis in brown, with a typical range between 10 and 14 seconds Phoebe. We will discuss later on about this test. And the development of the water content of the mix is shown above in blue on the right axis, as can be appreciated from early values up to 140 liters per cubic meter of free water content in the mixes. The optimization of the aggregates has reduced this value down to almost 105 liters per cubic meter in the last mixes. This 35 liters less water per cubic meter for the same consistency provides a large margin for the reduction of the content of cement and fly ash in the mix, aiming to achieve a certain level of strength. This aggregate is from a more fortunate RCC project where the source of material was a limestone quarry. Limestone crushed aggregate, including their limestone fines, is, due to its better behavior in fresh and hardened condition, probably the most adequate source for good quality RCC aggregates. Herewith, the main specifications for coarse and fine aggregates are shown including for the coarse aggregate on the left picture, less than 1% of dust coating the particles, and its cubical shape limited by a sum of flakiness and elongation index below 25%. On the right side, in a similar way as has been mentioned in the previous example, the high proportion of fines below 75 micron and the low void ratio of the compacted material are typical characteristics of an optimized fine aggregate. In this particular project, with a good quality source of material, the fine aggregate could be optimized in terms of both gradation and void content, thanks to the introduction of a vertical shaft impactor VSI type of crusher in the tertiary position of the aggregates plant. As can be appreciated in the figure, the blue line was the gradation of the fine aggregate produced with the first crusher. That resulted in high void ratio and water demands of the RCC above 122 liters per cubic meter. With the blend of that material and a natural sand, a significant improvement was achieved, as shown in yellow, with void contents below 29 and water demand less than 95 liters per cubic meter. The alternative with the VSI was the most optimized version of the three, as shown in black, indicating void contents below 27 and water demands less than 85 liters per cubic meter. Admixtures. Set retarder is nowadays the most popular admixture used, especially in high workability RCC mixes. The primary objective is to delay the setting time of the mix in order to be able to place the next layer within the initial set of the surface of the receiving layer beneath. The use of super retarded mixes, initial set of 20 hours or even more, is one of the key features of modern RCC mixes placed in large areas of, say, between 15 and 20,000 square meters, without any surface treatment, achieving a good bonding hot joint. This provides a huge placement efficiency, which is typical of the all RCC dam approach. An additional benefit is obtained by using these admixtures associated with a secondary effect as water reducers. Based on setting time tests made in outdoor conditions and according to ASTM C403, the figure shows the average relationships found in a particular project between the mean ambient temperatures and the initial set for different dosage of the retarder admixture. In this example, the line in black shows the selection in steps of increasing dosages of admixture as the ambient temperature rises, in order to keep at all times the initial set between 15 and 20 hours. However, the actual surface condition of the lift joint must be visually inspected at the placement by experienced supervisors to confirm the test results. The setting time is affected by other parameters, wind, humidity, mix workability, and so on, that are not always well identified in the test. These photos show typical good fresh condition of a workable and super retarded RCC. Note the print of the tires of the trucks used for the transportation of the RCC for the next layer. This is a good sign of the desired hot condition and the monolithic bonding between layers. Up to 9 different commercially available chemicals were used in a project to investigate setting time and water reduction in the mix. Lab tests, according to ASTM C403, were performed in lab and outdoor conditions to evaluate the performance of each one. Series of plots similar to this one were produced to determine the most appropriate dosage of each retarder. Note that in this figure the setting time at the left axis and the water demand at the right are plotted for each mix with different dosage. The position of the initial set between 18 and 24 hours in red would provide the desired dosage for the particular ambient conditions of the test. At the end, the parameters driving the final decision is a combination of these technical parameters, setting time, water demand, and other important inputs, such as the guarantee of the supply to the project and the general support given by the supplier, as well as cost. And in order to provide durability to the exposed surfaces of RCC dams, especially in cold climates, a number of commercially available air entraining admixtures have been successfully tested in a recent project with a very workable RCC mix. Dosages between 0.5 and 0.6% of these cementitious materials have achieved a very consistent air entraining between 4 and 7%, as shown in the figure above. Consistency and vivid test. Consistency as measured in fresh RCC with the loaded vivid test ASTM C1170 procedure B is a key control feature during placement. The result is the time in seconds that it takes to the paste under a standard external vibration to completely fill the edge of the disc placed on top of the concrete sample. The procedure should be slightly modified with full pre-filling of the mold and avoiding any previous compaction for very workable mixes, VB times below 12 seconds. Following the consistency test, the time of vibration in the test can be extended up to 2 minutes, and this produces a similar compaction effect, or just slightly below, as achieved by the rollers in a real placement condition of the 300 mm thick layers. Therefore, the test allows the evaluation of the amount and quality of paste that is brought up to the surface during vibration on top of the disc, as shown with number 2 in the figure. This is an excellent evaluation example of very good paste. Then it is all collected packed into the recipient, step 3, and the density can be measured as shown in step 4. The line diagram at the bottom right corner shows the position of different RCC mixes relative to the VB time, with stiff mass CVC on the left end. It should be noted the general reduction of this value in modern RCC mixes of all types compared with early times. We will be back with this diagram later on in another slide. As we started working in 2003 in a project called P in this slide for an RCC dam mix design, the specifications called for a 30 seconds VB time mix, and such mix should include all natural material from the available river alluvium in just 2 sizes, coarse and fine, without any processing. This case is represented with an A in the figure, and such mix would require 145 liters per cubic meters of free water, and no fly ash was recommended, although it was easily available in the country. To meet the design strength, it would have been necessary to use at least 135 kg per cubic meter of cement in the mix. However, such mix would have led to significant segregation at the placement. The reduction of the VB time aimed to increase workability with such materials would have raised the water demand above 150 liters per cubic meter. Following a value engineering proposal, some additional cost was proposed to be spent in an aggregates processing plant that would crush and classify the coarse aggregate. The cost of such treatment was worth, as the subsequent reduction in the water content was quite significant. The steps given during the laboratory design of the mix was with increased quality of the aggregate are shown in the lines labeled with B, C, D, E, up to the final solution F that was adopted for the construction of the dam. Mix F was designed with 2 partially crushed coarse aggregates from the natural source and 2 fine aggregates. One was produced by washing the natural sand, and the second one was a limestone filler delivered from an external nearby source. With such combination of materials, in addition to some other measures, the VB time could be lowered down to 15 seconds, and the final water demand was 112 liters per cubic meter. The lower water content led to significant cost savings in the project, enough to compensate the cost of the crushing plant, the addition of fly ash, and the admixture. For example, bedding mixes were no longer required between the layers to provide shear strength, and the upstream membrane was not required anymore as the concrete itself was impervious. Later on in 2015, in another project called here Project E, with a similar concept mix, but where a source of limestone quarry could be used to produce 100% crushed aggregate, a further decrease of the water content was possible up to 93 liters per cubic meter for an even lower VB time of 8 seconds in average. This exercise shows once more the use of the VB test to evaluate the potential improvements that are possible in RCC mixes during mix design. Typical mixture proportions. The average mixture proportions of the cementitious paste for different RCCs are included in this table. The content of Portland cement in first row is considered to be similar regardless of the RCC type. As has been mentioned before, the use of an SCM such as fly ash or pozzolan is actually the distinctive factor between low and high cementitious RCC, and the difference in this case is in average circa 100 kg per cubic meter. With regard to the free water content, it should be noted that the less workable low cementitious mixes, VBs up to 30 seconds and even more in early RCCs, is however higher, 122 liters per cubic meter, than the workable mixes with VB times below 15 seconds, with average 111 liters per cubic meter. It seems to be a contradiction. However, this actually shows that a significant level of workability can be achieved through optimization of the aggregates and the additional gain in workability provided by the use of pozzolanic materials and admixtures. This is even more evident when comparing the average water cementitious ratio of the low against the high cementitious RCC. While the mean value of 0.57 of the HCRCC in the right column is considered to be typical of mass stiff concrete, a water cementitious ratio of 1.51 in the low or even the 0.99 of the medium ones do not seem to follow the basic principles of traditional mass concrete. That is why other items additional to the RCC need to take part in the configuration of the dam in a separate approach. The additional cost of the higher total cementitious material content of the high cementitious RCC is by far well compensated by the other advantages relative to simplicity and less number of activities and mixes that has been mentioned in the introduction. The general procedure for the laboratory design of high workability super retarded RCC mixes is as follows. Step 1. The investigation of general material properties and confirmation of suitability as concrete materials, aggregate, cementitious materials, admixture, water. Step 2. Optimize the gradation of the coarse aggregate. Step 3, optimize the gradation and void content of fine aggregate. Step 4, optimize the overall aggregate gradation. Step 5, select an average proportion of cementitious materials for the preliminary mixes. Then we jump on to step 6, which is the determination of the water content to achieve the target workability as measured using the loaded VB. Step 7, investigate the dosage of different set retardant admixtures to meet the initial and final setting time criteria and modify the water content in each case as necessary to keep the consistency within the target range of loaded VB times. Step 8, evaluate the quantity and quality of paste during vibration. Make adjustments and fine-tune the amount of fines and the water content. Step 9, design a matrix of mixes with variations in the proportion and content of cementitious materials. Step 10, check the cementitious paste mortar ratio of each mix against the void content of compacted fine aggregate and other mix parameters. Step 11, investigate the development with the time of the compressive strength, cylinders or cubes, of the different mixes. This may include specimens subject to both normal and accelerated curing. Step 12, select 2 or 3 mixes meeting the laboratory compressive strength that, based on experience, is required to meet the in situ design criteria for direct tensile, cohesion, and compressive strength. Step 13, in case tensile strength is the critical design parameter, investigate also its development with the time for the selected mixes. And finally, step 14, conduct other laboratory testing for other specific mix properties as required by the dam designer that up to this stage could have been estimated from published data or experience. These tests may include adiabatic temperature rise, coefficient of thermal expansion, specific heat, diffusivity, modulus of elasticity, Poisson ratio, creep, strain capacity, shear strength, air content, and so on. In sum, 3 main groups of activities are developed in the process of RCC mixture proportioning at the lab. First is the investigation of materials, then the evaluation of the fresh properties of the mixes, and finally, the development of hardened properties. On finalization of the site laboratory tests, ideally only a single mix should be selected to be used in the construction of the full-scale trial, FST. In order to be able to reach conclusions, the trial placement should not be used to redesign the mix, but simply to make minor modifications and optimizations to the laboratory mix if found to be necessary through real-scale observation. The involvement of experienced personnel during the laboratory tests is important to correctly predict the behavior of the mix at real scale. As an example, a plot is shown here of the relationship in blue in a particular project of high cementitious RCC between the indirect tensile strength and the compressive strength as measured in laboratory cylinders, and in brown, the lower relation values between the in situ direct tensile strength as measured in cores and the cylinder compressive strength. Let's take now some time to introduce IV-RCC, immersion vibrated RCC. This picture was taken during construction of the full-scale trial leading to the construction of Spring Grove Dam in South Africa, completed in 2012. A very workable mix was designed with a VB time between 6 and 12 seconds. The mix has a total content of cementitious materials of 160 kg per cubic meter, of which only 50 kg per cubic meter is cement, and the remaining 110 counts for a local available fly ash. All concretes in this picture correspond to the same mix, and no grout, no mortar, bedding concrete or conventional concrete mixes are added. The spread and uncompacted RCC is visible on the right near side. The high paste roller compacted surface can be appreciated at the back, and the immersion vibration against the formed face is running on the left side, followed in this particular layer by a hand-held vibrating screed easily finishing the top surface of the future downstream steps. Immersion vibration is achieved without adding any grout and whilst the RCC is still fresh. The use of the set retarder helps also on this task. This is called immersion vibrated RCC, the most simple and efficient way of building modern RCC dams and its interfaces either against formwork, rock abutment, embedded elements, or dam instruments. Immersion vibration crosses the 300 mm thick layer and penetrates in total around 500 mm down into the concrete as shown here. In hot condition, when the second lower layer has not initiated set, this leads to a complete interpenetration of both layers and the elimination of the physical joint plane between them, achieving an excellent bonding and impermeability. This has been investigated by testing cores drilled in this and in the area compacted by the rollers. An excellent lift joint behavior has been observed in both cases. The key features of materials and mixture proportions of IV RCC mixes are listed in this slide. Most of them apply to modern super-retarded high workability mixes, as has been mentioned before. Special attention should be given to the optimization of the fine aggregate in this case in order to achieve a well-graded material and a compacted void ratio as low as possible, ideally below 30%. As this, as we explained, will reduce water demand and the required volume of cementitious paste in the mix. Example pictures of completed IV RCC dams are shown on the left. This is an excellent aspect of the stepped face built with IV RCC at the Hoop Dam in South Africa. And here a general view of the dam near completion. Just one RCC mix and no grout or conventional concrete against the faces or anywhere else. This is the completed Spring Grove Dam for which the full-scale trial was shown before. And this is Enciso Dam in Spain, a 103 meters high dam that has been recently completed and that is at present at the final stage of impoundment. The dam is showing an excellent performance and no seepage through the concrete. The same mix. The RCC that is roller compacted in the core is consolidated by immersion vibration at the faces against gallery walls, a detail is shown here, and also against the rock, with excellent performance. Vibrators mounted on an excavator manage high production and best quality. This core was taken crossing the contact and shows the bonding between IVRCC at the top and the rock in dark color at the near end. And this is a recent experience with air-entrained IVRCC. Note the high workability, rich in paste mix, and after immersion vibration on the right strip against an inclined formed face. It does look as conventional mass concrete, but actually is an RCC mix that can be vibrated by immersion. And this is a trial in which 3 different ways of forming the faces have been compared. Number 1, conventional concrete. Number 2, grout enriched RCC. And number 3, immersion vibrated RCC. No real difference between them. But IVRCC is much more simple and cost-effective option. Note that in this particular case, the IVRCC mix was also air-entrained. Air-entraining of RCC for durability is much easier with high workability mixes. This has been investigated in laboratory trials in a project located in a cold climate that was designed following early times RCC concepts with high cementitious RCC mix and conventional concrete CVC mixes against the formed faces and against the rock. Air entraining agent was required to achieve sufficient air content in fresh CVC. To avoid such sophistication, as well as potential quality issues with the CVC that have been experienced in other RCC projects, the alternative of raising up the workability of the RCC mix by slightly lowering the BB time was found to be an excellent solution. Initial specification called for up to 16 seconds VB RCC and a CVC below 50 mm slump. Well, with an alternative 6 to 12 seconds VB RCC, it was possible not just to vibrate it by immersion, but also relatively easy to get the required level of air entraining. Such alternative was shown previously in lab trials, including demonstration blocks of air entrained IB RCC, and later on in a real scale placement and course. But the most recent completed IVRCC dam is Enciso Dam in Spain that has been mentioned previously and for which we would like to give some additional details. This is a 103 meters high straight gravity concrete dam. Total crest length is 376 meters and the total concrete volume is circa 800,000 cubic meters. The upstream face is vertical and the downstream face with a 0.8 slope is stepped with 1.2 meters high steps. The dam is 8 meters wide at the crest and 81 meters wide at the base in the higher blocks. It has 3 horizontal gallery levels and a perimetric gallery following the foundation. The figure shows the different drain and foundation curtains specifications. The transverse joint spacing is 20 meters, except for 2 blocks of 15 meters that accommodate the width of the central surface spillway structure. Built in structural concrete, as it is also the river diversion and bottom outlet structure. The rest in the dam cross-section, except for some CVC leveling concrete covering the riverbed excavation, has been transformed from an original planned RCC plus CVC dam in a real all RCC dam built with IVRCC. Summarizing, the key advantages found for IVRCC at Enciso Dam are simplicity, just one mix is produced, transported and placed in the dam. Good quality, not just at the surface, but also in the contact interface between roller compacted and immersion vibrated areas. Interpenetration between successive layers of the vibrated concrete at the formed faces and against the rock. Excellent finish in the critical area at the upstream face around water stops. Similar development of the concrete properties, thermal, elastic, across the dam. More simple numerical models and simpler dam design. Speed of construction and economy. And this is a recent general view of the downstream face during impoundment. Let's summarize some key mix parameters for different types of RCC mixes. We will do that in a schematic way with values represented on linear diagrams. In all of them, as shown here for the consistency that we've introduced briefly before, the low cementitious RCC is placed on the right side and the more workable high cementitious mixes are located towards the left end of this line. The VB time is indicated in seconds. The drier, lean RCC mixes that were used in early days, particularly in USA and in Brazil, used to have VB times exceeding 30 seconds. Today, these mixes grouped as LC-RCC are, in general, designed for VBs below that value of 30 and down up to, say, 18 seconds. As has been mentioned before, when talking about materials, the need to control segregation is the main reason behind this modern trend of LC-RCC mixes. RCD, as built in Japan, and medium cementitious mixes are generally located next in this line, somewhere in the range of 15 to 20 or 25 seconds. And on the left side, you can see the high workability mixes below 15 seconds, with the very workable IVRCC below 12 and down to 6 seconds. These mixes are, in fact, touching the limits of zero slump CVC mixes. The next parameter is the in-situ density achieved by the concrete in percent relative to the theoretical air-free density of the mix. The relative density has been always higher in high cementitious mixes, which typically achieve a much better capacity of the materials. The indicated values are those usually found in the technical specifications for each type of RCC dam concept. Regarding immersion vibrated RCC, note its better density when roller compacted, in average higher than 99% of the theoretical air-free density, and slightly lower for exactly the same mix when vibrated by immersion. As it happens, this value around 98% is the typical one achieved in average with immersion vibration of well-designed conventional stiff mass concrete mixes, and a similar value is measured when vibrating IVRCC rather than roller compacting it. The so-called total paste volume of a concrete mix is calculated by adding the fines below 75 microns of the fine aggregate to the cementitious paste. The cementitious paste, as indicated on the left, includes the volume of cement, supplementary cementitious materials, water, admixture, and air. The total paste by volume is nowadays relatively similar in all types of RCCs. This used to be different in earlier times, but the addition of the fines has equalized this parameter. There are some extraordinary exceptions. On the very right end, the excellent IV RCC mix at Enciso Dam that was mentioned before has only needed 18.6% of total paste to achieve consistent VB times below 10 seconds. Let's take this example to better explain the maths behind this parameter. These are the mixture proportions of an IVRCC mix placed in Enciso Dam. Coarse aggregate is 1,444 kg per cubic meter, actual maximum size of aggregate 50 millimeters, 100% crushed. Fine aggregate is 778 kg per cubic meter of crushed limestone, which represents 35% of the total aggregate. The fine aggregate has an average at 12%, that is 93 kg per cubic meter of aggregate fines, or filler, minus 75 microns. Cement type 1 is 54 kg per cubic meter, fly ash is 126 kg per cubic meter, and free water content is only 84 liters per cubic meter. Therefore, total cementitious materials, cement plus fly ash, is 180 kg per cubic meter, and the water cementitious material ratio is relatively low, 0.47, similar to a CUC stiff mass concrete. A retarder admixture is used in a proportion of 1 to 1.5% of the weight of cementitious materials, and the mix is designed for 1% air voids, typical of high cementitious RCC mixes. Remember that the actual VB time achieved with this mix is 7 to 9 seconds VB. Well, transforming these weights into volume by dividing each respective value by the respective specific gravity and summing them up, we obtain the volume of cementitious paste, which in this case results in 162 liters per cubic meter. And if the aggregate fines minus 75 microns are added by volume to this sum, then we obtain the total paste of 186 liters per cubic meter. And this is where the 18.6% shown in the previous slide comes from. Going back to that slide, there is an additional important parameter that relates the volume of paste with the void content of the compacted fine aggregate. Since early times and for high cementitious RCC mixes, it was found that the amount of cementitious paste should not just fill the voids left by the compacted fine aggregate in the concrete matrix, but also to provide enough paste to achieve a reaching paste surface during compaction. If properly designed and protected in fresh conditions by adequate curing continuously and the next layer is placed on top, such excess of paste plays a major role in lift bonding. Experience shows that well-designed high cementitious RCC mixes have an excess of cementitious paste of circa 8 to 10% above the void content of the compacted fine aggregate, represented as VC in the line diagram. Conversely, the paste volume of early times lean RCC mixes could hardly fill the voids in the matrix, but nowadays, with the increased workability in all types of RCCs, most of them manage to bring some excess paste upwards to the lift surface during compaction. In the example mixture proportions shown before, the volume of cementitious paste was 162 liters per cubic meter, and the ratio to mortar calculated by adding paste and fine aggregate is as low as 0.35. Normal values of paste mortar ratio in other high cementitious RCC mixes are in the order of 0.40 or more. This particular and exceptional case is explained through the quality of the aggregate that has a very good shape and gradation, thus a low void content, as you may remember from this slide. Limestone fine aggregate 100% crushed in a VSI crusher and ending up with a void content of 0.26 to 0.27. Adding 8 to 9% excess of paste to these results ends up in a design value of just 0.35 for the paste mortar ratio. With this simple schematic representation of 4 key parameters, we were able to explain some main differences between various RCC mix design approaches. Obviously, each new project is different and needs advanced investigation and testing of the potential materials so that an optimum solution can be found for the project. There is no universal solution. There is no one solution that works in all cases. What should be bear in mind is that RCC needs simplicity in the design and during construction. Otherwise, the efficiency of the method is reduced, and in some cases it was found that if RCC conditions are not met, that in those cases, a dam like this, built with conventional concrete mix, slowly and in smaller blocks, might have been a better solution than RCC. And finally, let's draw some conclusions. Number one, high cementitious RCC is associated with high supplementary cementitious materials content mixes, whereas commonly low cementitious RCC mixes make no or very little use of such SCMs. Water content is even higher in low cementitious RCC. The quality of the fine aggregate, below 5 millimeters, and in particular the aggregate fines, below 75 microns, play a major role in the selection of the mixture proportions for RCC mixes. Conclusion number 2. Key common features of all kinds of modern RCC mixes are a reduction of the maximum size of aggregate below 50 millimeters to control segregation, a volume of total paste, including aggregate fines, between 210 and 240 liters per cubic meter, which means 21% to 24% by volume, and improved consistency, lower VB times relative to values used in early dams. And number 3, high workability RCC mixes simplify dam construction and achieve best in situ properties. Immersion vibrated RCC, a mix that can be consolidated either by immersion vibration or roller compaction, is the most optimized version of very workable and super retarded mixes. IVRCC means no CVC, no bedding mixes, no grout, just RCC placed in the dam. And thank you very much for your kind attention.
Thank you for making an excellent and detailed presentation on material and Thank you for making an excellent detailed presentation on material and mix proportioning. Do we have Mr. Francisco Ortega present so that we may proceed further for the question answer session?
Yes. Hello.
Okay, thank you. Thank you, sir. Thank you for your confirmation. May we proceed further for the question answer session? May I request to the participant for their questions, please? Yes, Mr. Anil Jain, please. Sir, you are muted. You are on mute. Kindly unmute yourself.
Thank you, Mr. Ortega. I have some doubts which I would like to have clarification from you. First of all, like you said, we use in high cementitious RCC SCM of the order of, say, it may be more than 100% of cement content. So what is the best method of mixing them at site, cement plus SCM, or it is at factory level with cement clinkers and SCM? What is your opinion on that?
Okay, thank you very much for your question. I hope you can hear me properly.
Yeah.
We did. Okay, thank you. Well, the answer to your question, of course, depends on the quality of the material you intend to use as supplementary cementitious material. I mean, if you have a uniform product that you see that you can use it uniformly through the construction process. I, in this case, do prefer much more to have the mix made on site, so that you have a better control of the combination of the blend of cement and the supplementary cementitious materials. Sometimes the variability of the original product needs some pre-processing, and this pre-processing in some cases, and depending on the culture of the country where you are doing this job, it is necessary to make this pre-processing and blending it with the cement in a cement factory. Okay, but in principle, I think the optimum solution would be to have this blend on the site.
That side. Okay. So when we have this PPC, there is the upper limit as per our caudal provision that you should not have more than 25% pozzola in PPC. So when we do in this case, we have pozzolana more than 100% of cement content. So how it means, what is the difference there in PPC where limit where we mix it at factory level, that limit is 25%, and in RCC case that is there is no limit of that.
Exactly, that is the case, and that should be the case, because we have been using pozzolanic materials, supplementary cementitious materials, as you saw in the presentation, up to 70-75% of the total cementitious material content. And this is necessary to provide better quality to the mix in terms of many things. I mean, there are, for example, a lot of good quality fly ashes that help to reduce, because the shape of the particle of the fly ash help to reduce the water demand. The significant reduction in the heat generation of the mix. You know, there are many advantages which bring us up to use as much as possible of this supplementary, if at all possible, of course.
But why in PPC that limit is 25%?
Yeah, where is that limit in your country? Yeah. I mean,
do it need revision?
Not for RCC, definitely not. I mean, for RCC,
we know in RCC it is 70%, 75-80%. So okay, and then you said in all your presentation target strength at 365 days. When we do it for trial mixes, do we take it at 365 days or at 28 days?
Okay, thank you. Very good question. The analysis of mixes in the laboratory, the previous analysis that we described, needs to somehow investigate the mixes in a short time, but giving us the tendency, the trend to the long-term performance. So that is why in many of these processes, we need to make accelerated curing of the specimens so that we can have an idea of the long-term strength performance of the mix. And that is why we do that, and we are able then to predict what will be the strength at the design age of 1 year, which is not always the case. I mean, it is very generally, of course, 1 year, because then you take full advantage of the supplementary cementitious material that provides strength at the long term, and not only the short term. But there are some projects, and I want to mention this as well, where the 90 days strength, for example, is important. There are some projects in cold climates where you build the RCC in summertime, and the concrete is generating heat, and the heat is remained in the core of the dam. At the surface, during the first winter, it cools down. And in those cases, you need some strength in this concrete at 3 months, so that you can really support the stresses of this thermal action, which happens to be very early in the time of the concrete.
So what ratio we use for converting 28 days strength to or 90 days strength to 365 days? Is it same as CVC, or
No.
It is differing from that?
It's different mainly because you are using so high proportion supplementary cementitious material. So you need to investigate this, and this is important. What I said in the first slide, the investigation of the materials for each particular project and each particular conditions need to be done well ahead of the initiation of the construction, because there is where you save, so you don't have surprises, you save money and cost and economy for the project to do that well ahead.
Okay. And this is regarding IVRCC. When you said we use it for facing or we use it for entire dam?
Yeah, that is IVRCC is the RCC which is vibrated by immersion vibration. And this vibration of the same mix that you do roller compaction in the core, you do vibration at the edges. So the same mix.
Sorry. Then how does it, this VB is different for these two, core and facing? Is it same?
The same mix with the same VB.
Okay.
Okay, and the VB range 6 to 12 seconds, and then you manage to get it roller compacted, and at the same time, in the same very minute, you are vibrating the same mix against the formwork.
Thank you very much.
Okay, thank you for your questions. Thank you very much. So happy to answer any other questions.
Yes, we have the next question from Mr. S. Chaudhary.
Yeah, can you hear me?
Yes, absolutely.
Thank you.
Yeah.
Yes.
My question is whether a limestone dust can be used as an SCM. And the second question is the strength you have shown, the laboratory test tensile strength and compressive strength, how they are related to field strength, means how much degree generally is it field, can we achieve 90% of that or more than that? And one more question, the for shear strength determination, what kind of test you recommend? Is triaxial test on cores will be a good option or a direct shear test?
Okay, thank you very much for your questions. To number one, limestone filler has been used and is used in RCCs. We have found two different performance of this limestone depending on the quality of the limestone and depending on the quality of the rest of materials which are in the RCC. And limestone has been used to fill voids because the natural sand that we probably were using did not have enough fine, so we filled voids with this filler, and it was good because filling voids with a filler does not have a direct relationship in the strength because it did not act as a cementitious material, but had a big influence in the reduction of the water demand. Less voids, then you have reduction. So by reducing the water demand, you could reduce the cement and any other supplementary material that we are using. However, there have been some projects, and depends again, as I said, in the quality of the filler and the rest of materials, where the filler showed some cementitious activity. I would not say puzzolanic activity because puzzolanic activity has the connotation that it will be a long-term strength performance, and the filler is a calcareous material, normally what we use. It does have some cementitious properties, but more at early ages than long-term ages. So both things happened. So I hope I answered your first question with these two comments. The second, about the compressive strength. When you go to the field, you find a big range depending on the quality of the mix which came out of the laboratory. I mean, we have had reductions in compressive strength which are very big in the field if the material segregates, for example. You don't see this in the laboratory, but you see that on the placement, and then the core compressive strength is much lower, as low as 50% or even more lower. However, in the good, well-designed mix in the laboratory, when you go to the field and you get the compaction and you get the paste out when compacted, then the material behaves much similar as you had in the laboratory. And 100% compressive strength as in the lab, probably not, because you have also the drilling activity of the cores also affects somehow the strength of the concrete. But I say 90% of that strength you can easily consider and achieve. What does it not mean that probably the concrete which remains inside has a strength of 100% or even more. The problem is you don't get to that value through drilling. Okay, that was the second question. And about shear strength, you were asking and testing. So we've talked, depending on the project and the time that we had and the economy of that we had available, we made the two tests that you mentioned, either direct testing with shear blocks and testing on real scale placement. That was possible to be done, but it has been also done through cores. And this has been done through incline cores at different angles, and then making compressive strength of that particular core, which takes the joint that you try to test in an incline angle. So if you have two different cores in two different inclinations, you can calculate the maths and calculate your cohesion and angle of friction, which is something which has been done, but more specifically for cohesion, because angle of friction, we know nowadays it doesn't change so much from mix to mix. So I hope I have answered your three questions.
Yeah,
Thank you very much.
one more question, because I
Sure.
have involved in some trials recently. What I see is how much for triaxial test, how much cell pressure do we need to give? How much cell pressure do we need to maintain? Is it the does it depend on the normal stress of the dam which we expect? You give a cell pressure and then a deviatoric pressure in a triaxial test. Maintain how much values of the cell pressure to maintain, because as we increase the cell pressure, the apparent relation of cohesion and the angle of internal friction changes. Means at higher cell pressure you get very high cohesion, low friction angles. At low cell pressures you get low cohesion and high friction angles. So how do you adjust the cell pressure?
Yeah, this is a very particular question, which if you like, you could then write directly and we can answer that, because you are entering in a very particular exercise, which I agree with you entirely. I know exactly what you're talking about, but it would be long and difficult to explain through this method. So if you agree, but I mean, this has been done and there is experience about this. No problem about that. Okay, thank you.
And the clarification regarding the earlier question asked by one of our earlier who have asked the question, why the 25%? From what I know, I just want to clarify the 25% PPC limit has been kept to achieve the 28-day strength vis-a-vis OPC. Means since adding PPC delays the strength gain, so it has been seen that up to 25% or 30% somewhere, you can match the 28-day strength with OPC. So from building design considerations and that part, even it is, I think it is also mentioned in USBR RCC manual, this range. So this is one clarification from my side.
Thank you, Mr. Chaudhary. Thank you, Mr. Chaudhary.
We have the next question from Mr. Arun Pratap Singh.
Hi, sir. Seepage is invariably a huge problem in normal conventional dam, whether it is gravity dam or embankment dam. How does the RCC dam is different from these two dams in terms of seepage? I mean, how can we control seepage in these dams? That's and assessments regarding the seepage value tentative.
Okay. Sorry, I would repeat what I understood because it was cutting somehow. So if you can confirm, you're asking about seepage in RCC dams, the control of seepage compared to CVC and embankment dams?
No, sir. I'm asking seepage of RCC dam in comparison to normal conventional dam, whether it is gravity dam or embankment dam, oblique earthen dam.
Okay.
You are getting my voice?
Okay, but say seepage, huh? Seepage,
yeah,
water seepage. Yeah. Okay. Thank you. Yes, I think I got it now. Well, the concrete itself, the RCC, if it is well designed and properly constructed, is an impermeable material, as it is the conventional mass concrete in a conventional mass concrete dam if it is properly designed and properly placed. So this seepage through the dam in an RCC dam should not be higher than it would have been in a conventional concrete dam. However, there are some concepts of RCC, as we have seen in the presentations so far, where the RCC material itself is not impermeable. There is seepage through the material, and mainly not through the matrix, but across the joints between the different layers that, remember, you place layers every 300 millimeters, so there are many more joints in RCC than in CVC. Therefore, the critical point for seepage in RCC dams, which has not a mixed design properly done for bonding between layers, is this seepage through the horizontal joints between them. And in those particular dam designs, you need to create some impermeable activity, some impermeable material at the upstream side. And it was in the past used a different mix, like a conventional concrete. We have seen also in those dams that you use an upstream membrane. But as I say, this, and I have said that in the presentation, if you heard that, this makes a more sophisticated design and construction, and it is against the main principle of RCC dams of simplicity. Therefore, we recommend that the mixed design, if at all possible, should be done in a way to get at the placement an impermeable material. So this is how you can compare, in that case, RCC and CVC, because CVC is in principle an impermeable material, as the joints between CVC blocks are also impermeable. So I hope I could answer your question.
Just follow-up question. Suppose, we are getting high seepage in RCC dam. So how can we treat at later on stage when the reservoir is full?
Yeah, good question. And of course, there are some companies around the world specialized in grouting such kind of seepages of RCC dams, and they are happy that you have problems in your RCC dam so that they can make their business. But this should not be the aim of your original thoughts. The aim of your original thought should be to make a proper dam which is impermeable and doesn't need the action of such grouting and such treatment, which, as I said, there are enough solutions in the market in case you have cracks or seepage through horizontal joints that you can treat. It is, however, difficult in case you have a lot of seepage through horizontal joints to treat them fully. No doubts about that. I mean, it's easier to treat a vertical crack or incline cut, but the horizontal joints are definitely difficult to treat, although it has been done and can be done with a lot of cost.
One more question. In one
Sure.
of slides, you said that you are reducing the aggregate size from 90 mm to 50 mm. While doing so, actually, we will be getting more heat of hydration. So how will you tackle that, particularly in India, where in summers temperatures are more than 40 degrees Celsius, 40 to 50 degrees centigrade Celsius. In Fahrenheit, you can say 104 or more than that.
Yeah, I mean, the reduction of the maximum size of aggregate in RCC is there should be no discussion anymore about that. I mean, it's really necessary in all kinds of RCCs. We need to fight against the segregation problem, and the reduction of the maximum size is the solution for that, in addition to the workability and the consistency. If you go to the in situ properties and the strength of the concrete, when you reduce the maximum size of aggregate, according to conventional concrete principles, as you say, you're thinking we will need more cement, we will have more heat of hydration. But in fact, by reducing the maximum size of aggregate in RCC mixes, you also reduce the water demand. And I go back to what I said before. By reducing water demand, you reduce the cementitious material. So in fact,
what we have experienced is the opposite, as in CVC principles, CVC concrete principles. You reduce the maximum size of aggregate, and to achieve the strength on site, you also can reduce cementitious material content. You see, so it looks a contradiction from conventional concrete principle, but it is not. We get a much better in situ properties by reducing the maximum size. Therefore, you can reduce the cement content.
Okay, sir. Thank you, sir. Very insightful presentation.
Thank you very much. Thank you.
If the participants have any further questions, I would request them to write to us, the organizer CBIP, through the email, so that we will revert back to them after getting the response from the respective speakers. Thank you, participants, for such an interactive question-answer session. I would like to convey my special thanks to Mr. Francisco Ortega for sparing his valuable time for conducting this virtual session. I'm sure all the participants must have benefited from his vast knowledge shared during the program. Thank you so much, sir.
Okay, thank you very much to you and for your wonderful organization of this event. Thank you very much.
Thank you, sir. See you all, the participants, tomorrow for day 3 session at 1100 hours IST. Thank you all. Stay safe, stay healthy. Goodbye.